Hello, today we'll be presenting our Pi Baseball machine learning project. This is Frankie Scullin, Mark Pepai, and Robert Reitz. And yeah, hope you'll enjoy.
Getting into the introduction, basically we created a scenario where we were hired by the Yankees to create a statistic or a methodology for finding undervalued players. Analytics has been a hot topic in baseball. It's something that's very, very important and also very, very valuable. Firstly, teams spend about $8 million in free agency acquiring new players to win one game. And also, if you do end up completing the goal of the season, which is to win a championship, this year the Dodgers won $35 million for that. So obviously there's a lot of money to be made in analytics and making your team better. Something recently in analytics, baseball analytics, that I thought was really cool was that the Yankees have created something called a torpedo bat, where essentially they take the wood from the top of the bat, called the barrel, and they move it down to right underneath the barrel. And they do this for players that don't hit the ball up here very much and have a lot of contact with the ball down here. And they partnered with a physicist and statistician from MIT to do this. It's been a 2-year-long process. And they just started doing this this season, so we don't really know the effectiveness of it yet. However, it will be something cool to keep an eye on. And essentially what we're going to be using is the Pi Baseball data set, which has data going back to 1876. And we're going to be using k-nearest and regression to calculate batter value. We're going to classify them using a neural network and then figure out which ones perform best at our stadium using a random tree. And this graph essentially just says the number of baseball analysts and data engineers per team and how many games they won. As you can see, there's a pretty significant positive correlation between the two. So good teams use a lot of analytics and they pay a lot of people very well to do them. So, very basic overview of baseball. 4 types of hits: single, double, triple, home run. The other outcomes are fielded out. The defender successfully fields the ball, a strikeout, you fail to hit the ball, a hit by pitch where the pitcher hits the batter with the pitch, and a walk where the pitcher fails to deliver competitive pitches to the batter and the batter gets to go to first. An overview of stats is there's batting average, which is a rate stat, just hits divided by how many at-bats they have. On base percentage, which includes walks and hit by pitches. Slugging percentage, which adds a weight. It's essentially a weighted batting average. You can see the weights there, so 1 for single, 2 for double, etc. And then weighted on base average is what we're going to be trying to predict. It is a statistic that applies weights that directly correlate with the ability of a batted ball event and a walk and hit by pitch to produce a score or a run. And so it's a more accurate description of actual value from every event. So the problem with those stats is they're descriptive. They tell you what happened, and we want something that will be predictive and tell us what will happen in the future. And the biggest problems with this in baseball is this idea of luck, I guess you could say. One, the hitter has no control over the quality of defense. They have no control over weather factors, like, if it's raining, it might be harder to hit. If it's windy, it might be harder to hit. And then there's something called chaos, I like to call it, but just a lot of very crazy things happen on a baseball field. Another idea here is park factors. Essentially, every field has different dimensions. There are different altitudes, they have different weather conditions, and these all affect how the batter hits the ball. And these are some examples. So this guy in the same game hit the shortest home run ever tracked in the StatCast era. And then 2 innings later, he hit the second shortest one ever tracked. Pretty crazy. This is the longest ball that's ever been hit that didn't go for a home run because of the 50-foot wall in the outfield. This ball was a home run until the guy jumped over the fence and caught it. It's pretty crazy. I made it realize I got unlucky. The designers of this ballpark decided to put a hill in center field. Nobody's really sure why, but it's something that happens. Here is some pretty terrible defense from 2 very, very good players. Here's some very good defense. That's the hardest ball ever hit, and it led to 2 outs. one of the softest balls last year to go for a hit, and he got a double off of it. He didn't even need to swing at that. And here's a peak example of chaos. The ball actually hits off the guy's head and goes over the fence for a home run, which is pretty crazy.
As Robert mentioned, we're using the Pi baseball data set, which combines three of baseball's most robust data sets, and it's an extremely large data set. Savant is a more predictive data set. Fangraphs and Baseball Reference they have descriptive statistics. And this diagram here shows, it's a heat map, it shows a launch angle versus exit velocity. And essentially, it's showing the optimal launch angle and exit velocity that you can hit. You see here the WOBA is maximized right over here at the launch angle and exit velocity near 116 and 30 degrees. So that shows like the optimization.
And just so briefly, we use ordinary least squares to estimate WOBA weights. For all of our calculation, we use the Fangraphs weights that they provide just for consistency. However, we thought it'd be interesting to try and recreate them. Fangraphs does not use linear regression. They essentially have access to millions of data points and these very, very powerful computers, so they can just do it like just manually, basically. But we use linear regression. We got pretty close to the actual weights. So we thought that was really interesting and just something cool that we tried. So essentially what we used for the XWOBA preprocessing was very simple. We took the StatCast data set, which is full of a bunch of predictive statistics, and we took the data that we thought, or we know, is most important for when a ball is a hit, a double, triple, home run. This is launch speed or exit velocity, launch angle, and then we took these coordinate system, HCX, HCY, and when we did that is we centered the coordinates around where the batter hits the ball from, and then calculated a spray angle, essentially what direction the batter hits the ball. We discretized this spray angle because essentially batters have an ability to generally direct where they hit the ball, but they don't have an ability to choose where they hit it. So we thought it would be more appropriate to discretize this data. And we also had to replace the player IDs with player names to make it more readable for people.
We actually use a different data set for our archetype preprocessing. We use batting stats, which consists of averages of each player's main hitting statistics throughout the season. We chose the 2024 season. And we chose our relevant columns, pull, oppo, cent, ground ball, strike percent. Pull, oppo, and cent are basically the direction you hit the ball, like where in the outfield. Strike and walk and hard hit. Hard hit is basically just a power stat, like exit velocity over 95. We standardized the data, which is necessary for the autoencoder used later on. And then we took batters with 80 or more games played because players with too low games played skewed the data. And we introduced a stolen bases per game stat. We wanted to do per game because even though we're doing 80 or more, there's players with 80 games, there's players with almost every game, and we want to make it consistent throughout. And this adds a speed element because that's another part of an archetype is how fast they go. So
Based on what Frankie did with the archetypes, we wanted to find out which archetypes perform the best, and before we do that, we have to do some pre-processing. So of course we have to merge the data he found, the archetypes, with XWOBA data and player names. We introduced a performance column. Essentially what it does is it takes the archetypes and gives them a ranking based on the XWOBA, so that we can use that. Once we do that, we can use the one-hot encode. What that does is it takes categorical data or text label information and it encodes it into a numerical information, basically, so the machine learning model can use that information, the archetype information, for its processes.
Okay, so here I get into how we calculated our XWOBA, which is expected WOBA. We used the K&N regression. I'm sure everybody is familiar with K nearest neighbors. Essentially, we take a data point and we look at the K nearest neighbors and we say, okay, well, the majority of them are red, so we're going to classify this data point as red. What K&N regression does is essentially it looks at the data points around it, and instead of giving it a classifier, it gives it a continuous value that is essentially the average of all the data points around it. So essentially, like we said before, exit velocity, launch angle, spray angle were inputs. Our output was expected WOBA, and we validated our technique using k-fold cross-validation, which is what we did for all of our models. Bootstrapping here doesn't really apply because we have such a large, robust data set, and bootstrapping is for smaller data sets. Our accuracy was, we had a 55% improvement over the Fangraphs model, which we believe is solely because of the implementation of spray angle. However, some other ideas that could happen is that essentially these guys at StatCast, this is their profession, they have PhDs, masters in statistics. They know what they're doing, and it is possible that we turn XWOBA, which is meant to be a predictive statistic, into a more descriptive statistic by introducing spray angle. This is something that would need more investigation, and more investigation beyond just k-fold cross-validation or any normal machine learning techniques. And also, it's possible we overfit the model. We think this is a very, very low chance because we did do a lot of validation methods. And then we applied this model to Yankee Stadium. We essentially simulated the season as if every game was played there. And we found that our biggest winner was Patrick Bailey, as his batted ball data was 14% better at Yankee Stadium. And our biggest loser was Tyler Fitzgerald. As you can see there, he's very, very sad about this, as his batted ball data was 29% worse at Yankee Stadium. So some hitter archetypes. The reason we want to archetype the data is very simple. Not every hitter provides value in the same way, and we want to be able to encapsulate all of the ways that hitters provide value. And we also want to encapsulate how do different hitters and different characteristics of hitters change based on the park factors. You can see here, this is a GIF of some, essentially, our different archetypes, some notable players from each archetype. And here are our archetypes. It essentially boils down to this. There's contact hitters and there's power hitters, and there's disciplined hitters, meaning they walk a lot, and non-disciplined hitters, meaning they strike out a lot, they don't walk, basically. And also there's the speed element here with fast power hitters. This is actually a pretty big data set, or archetype, because the speed that generates power correlates to the speed of running the bases.
So getting into the methodology of our archetype classification, what we did was we used an autoencoder, which is a neural network that does dimension reduction. So if you compare this to the PCA does kind of linear data, linear dimension reduction, while the autoencoder can do nonlinear dimension reduction. And we wanted to use this here because our data is interacting in nonlinear ways, it can also, by doing this dimension reduction, kind of separates the clusters more, where it hones in on the most noticeable trait and gets rid of noise. A good metaphor for an autoencoder is like a piece of origami. So you have your flat paper, you encode it by folding it into origami, and then you decode it, but when it comes back, it doesn't have all the data, it has wrinkles in the paper. So it's not a completely accurate representation, but it's kind of still the key thing. It's still paper, but you're still trying to keep the key idea. And this is some of the plot I did in my code where it shows the original sample, and then see like the kind of crevices here and things. It kind of just kind of makes them more flattened out. Like, it's still very similar, but it kind of straightens things out more. So yeah, so that's what the autoencoder does. And then yeah, after the autoencoder was mainly for setting up the clustering, and then afterwards we did clustering using k-means. So what k-means does basically is it randomly assigns these things called centroids, which it updates as it goes on. So this is a good graphic demonstrating it. So you can see the centroid updating. So the centroid kind of is the mean of all data points in that cluster, and then basically using Euclidean distance, it decides what's in what cluster based on how far away it is. And then here you can have a visual representation of, this was from our Python code, kind of showing the clusters it made, how it's organizing the data, and how it was replicated in the testing set. And then for interpreting our data, this kind of shows the stats per cluster. So for example, cluster 1 has, I'm colorblind, so what's this one? Cluster 2 has the highest pull percent, so that would be in the pull hitters cluster. So yeah, so we kind of use this graphic along with, we printed out the averages for stats along the cluster to kind of decide, all right, how are we going to name these clusters? And Robert, the baseball nerd, did most of that. So yeah, that was our cluster.
After classification using k-means clustering, we wanted to apply these archetypes to Yankee Stadium and figure out which archetypes perform the best in Yankee Stadium. To do this, we used the random forest classification. Basically what random forest does, it's many decision trees which each see a random subset of data, and they learn which archetypes are correlated with higher ex-boba values. And they learn these rules on how to, well, they learn these rules, for example, if the archetype power is lower than 0.5, then it ranks lower, and if it's higher, then it ranks higher, performance rating that I mentioned earlier. And essentially it determines a usefulness factor or an importance factor, which is related to the ex-boba and the performance ranking for each archetype. This graphic here is essentially showing the relation between importance and archetypes. As you see, the free swinging power archetype ranks the highest, and something like pull contact hitters rank the lowest. And this makes sense for Yankee Stadium because left field is quite long, and right-handed pullers tend to swing to the left of the field, so they get less home runs. So random forest is essentially finding a correlation between the magnitude of ex-boba and an importance factor. And higher importance corresponds to higher ex-boba and better player performance. And in this way, players can be chosen based on their archetype instead of just their ex-boba.
Alright guys, so I'm going to hit you guys with some conclusions, some things that we found, some takeaways from this final project. So, for K&N regression, we essentially found that our introduction of spread angle really improved the efficacy of ex-boba. It made it a more effective stat, and it was better than the current public models. Here again are the archetypes that we found, and we found that these free swinging power hitters perform best at Yankee Stadium. Essentially guys that hit the ball very hard, but they strike out a lot, they don't walk very much. These guys had the best batted ball profile improvement at Yankee Stadium. Our recommendation is to sign Patrick Bailey. Look at him, he's very happy about this. He wants to be a Yankee, a big Yankee fan. We think he'd be a good signing because essentially his batted ball profile performs much better at Yankee Stadium than it does at an average stadium, so we'd be able to get more value out of his production. And some areas of further investigation. One, we'd want to further investigate our introduction of spray angle on the upcoming seasons to ensure that it still maintains the predictive nature of ex-boba and doesn't make the stat too descriptive. We also would like to improve batter archetype classifications. Essentially, we would first want to try using a supervised model, and currently use an unsupervised model for our clustering. We'd try using a supervised model. And we want to try what we decided to call a multi-layer classification. What we found in a lot of these, in classifying the batters, was this pattern of where, pull contact hitters, but then there would be another class that doesn't essentially include the pullness of the batter, or how pull contact hitters got skewed because a right-handed hitter and a left-handed hitter pull the ball in different directions. So we'd want to introduce handedness. We split the batters by right, left. And then we want to try to classify the hit direction, how often they hit it to the pull side, center, and opposite field. And then we try to classify batted ball profile. We think this would be a more robust way of classifying our hitters, and it would definitely be something that would improve upon our classification, and it was an idea that we came up with. Yeah, that was kind of weird. Thank you for listening to our presentation. Hope you learned a little something about baseball. Anyone else watching at home, hope you learned a little something about machine learning. It was a fun project. Dr. Digwe, thank you for the great semester. It was a great class. Have a nice summer.
Thank you.